We're continuing section 15.1, functions of more than two variables. We introduced functions of two variables, z equal to f of x and y, where x and y were in D. And note this is they belong to D, that it's called epsilon or belong to, and D subset of R2. That other notation is a subset. D is the domain of f, the set of all possible input values. The range is f of x and y, where x and y belong to D. And then the graph of f is x, y, and z, where x, y belong to, again, that sign is belong to D, and z is equal to f of x and y. So these were the functions of two variables. How about functions of three variables? For three or more, let's say w equal to f of x and y and z, or y equal to g of x1, x2, all the way to xn, and many inputs. The domain and range of these functions are defined in the same way. The domain is the set of all possible inputs, and it follows the basically, for this one domain is in R3, and this one domain is in Rn, so in n-dimensional space, and the range is set of all possible outputs. And these are all scalar functions, so they only have their range is subset of R. However, their graph are difficult to visualize directly, so it's not functions of two variables are easier to visualize. Of course, function of single variable functions are always easy to visualize, but more than two are very difficult to do. For functions of two or three variables, we use contour maps as an alternative means of visualization. So let's explain what contour maps. Level curves and contour maps. Given a function z equal to f of x and y, the level curves with level k is L sub k of f, such that x and y in D, and f of x and y is equal to k. And so is the set of all x and y in D, such that f of x and y is equal to k. So basically you're looking at the level at all z values that are equal to k, and you go back to the domain. Like right here, you look at all the z values in the and z values equal to a constant, and then you look at the image of that in the domain, or projection of that on the domain, which is going to be the domain of that curve. Basically, a contour map is a collection of several level curves in D. And it's used to represent a three-dimensional graph as a two-dimensional figure. And so you've seen this in maps. Like in maps, you see all these contour map. You see the contour map, and you see all these level curves that tell you what is the altitude at certain places, and then you sort of get an idea where is the highest, where is the lowest, and so on and so forth. If you remember from when we were graphing the surfaces, at some point we discussed to put all the cross sections, the curves that you get from cross sections together, and it gives you an approximate shape of the graph. In case that there was a graph of a function, or a piece of it was a graph of a function. And so that's the same concept. You can imagine how it's just as if you pull it up, and it becomes a surface rather than something on the XY plane, flat on the well, I guess XY plane is a surface too, but it becomes a non-flat surface if you pull it up, and that's what you imagine in here as well. So example 4, sketch a contour map of z equal to f of x and y, and f of x and y equal to x squared minus y squared, with levels k. K can be 0 or plus minus 1 or plus minus 2. So k belong to the set of those. So how many? 1, 3, and 5 level curves for the contour map. If you set x squared, so what you do is you set z equal to any of these k values, right? So if I set z equal to 0, and that's the first one, so z equal to 0, then it would give me x squared plus y squared is equal to 0. And solving that, you take one of them to the x squared, minus y squared equal to 0. You take one of them to the other side, and you get x squared is equal to y squared. Therefore, x is equal to plus minus y. Now, second level curve. Let's say the x squared plus y squared equal to 1 by setting z equal to 1, and then or for the third one you can set x squared minus y squared equal to 2. These two are both parabolas opening horizontally, and then if you do the other two, those are parabolas. If you set z equal to -1, z equal to -2, those are parabolas that are opening vertically, and so the shape is going to be like this. For k equal to -1, you get these two branches. K equal to -2, you get these two branches. K equal to 1 gives you these. K equal to 2 gives you these, and k equal to 0 gives you that. And this is actually a contour map of the saddle point or parabolic hyperboloid. iClicker question 15.1a are the following statements true or false? The contour map of f of x and y equal to x and g of x and y equal to 2x are identical. Two different level curves of a function may intersect. Give yourself a little bit of time and imagine the contour map without any k attached to it, and so would that then make the contour map of f and g to be identical? So let's say for these two to be identical, they have to have the same curves. Remember, we're not putting any label on them. You only label when you that's another part of the making contour map. So let's say if I have f of x and y, if I set z equal to 1 for the first one, and then I get x equal to 1 as a level curve. How about if I set g of x and y equal to 2? Then I get 2x equal to 2, so I get x equal to 1 is a level curve for g also. And vice versa, if I set 2x equal to 1, I get 1/2, and then x equal to 1/2, x equal to 1/2 a level curve for g, and it would be a level curve for f as well. So we're going to get the same level curves. They have different labels, so the contour maps are identical. How about can they intersect? As for intersection, two different level curves of one function this time, not two different functions, can they intersect? Let's imagine level curve z equal to k sub 1 and level curve z equal to k sub 2, right? Because it's a function, it can z equal to k1 and z equal to k2 cannot be assigned to the same x and y point, so they cannot have an intersection. So 1 is true and 2 is false, and that's C. Let W be f of x and y and z, be a function of three variables with domain D, and let K be a constant. The level surface with level K is L sub K of f as x and y and z, all x and y and z, such that f of x and y and z equal to K. L sub K of f is typically a surface in D, but can be sometimes smaller than a surface. And so let's look at what we mean here. Let's say function is f of x and y and z, and x squared plus y squared is equal to x squared plus y squared plus z squared. So the function is function of three variables. That the example is a function of three variables. If I'm setting the function equal to the rule of the function equal to constant, like here, x squared plus y squared plus z squared equal to 1, x squared plus y squared plus z squared equal to 4, x squared plus y squared plus z squared equal to 9. Every time I get a sphere. And so these are the level curves of the functions of three variables, scalar functions of three variables. The scalar function of three variables. So the last example, the level curves level surfaces were very familiar. And let's do a few examples that level curves are a little in maybe something to notice in the last example also, that if you had found the level curve for k equal to 0, you would level surface for k equal to 0, you just would get 1 point. So the level surface would be just a point, not a level surface anymore. The level and that's why sometimes we don't call them level surface or level curve, we call them level object basically. Now let's do another example. Example 5, sketch a contour map for W equal to f of x and y and z, where f of x and y and z equal to x squared over 4 plus y squared divided by 2 minus z squared, with levels k belong to 1, 0, and -1. So first let's put in 1. If you plug in 1, then the level surface is going to be x squared divided by 4 plus y squared divided by 2 minus z squared equal to 1. And then this is going to be a hyperboloid of one sheet, because if I take z squared to the other side, again, if you remember, cross sections exist for every z. Now if I put this equal to 0, x squared divided by 4 plus y squared divided by 2 minus z squared equal to 0, then and take the z squared to the other side, I get a cone. And then if you set it equal to -1, you get hyperboloid of two sheets. So the picture, if you see, the red one is the hyperboloid of one sheet. We sort of got rid of the front of it. You just see the outer part. And then you see the blue is the cone, and then the yellow is the hyperboloids of two sheets, and exist over here, exist down there. iClicker question 15.1b. Match the function with its contour map. F of x and y equal to 4x minus 3y. So pause your video and come back and answer the question. So hopefully you pause your video and now you're figuring out that all the contour maps are going to be, you can plug in whatever value for k. For example, I can plug in k equal to 0, or I can plug in k equal to 1 or 2, and I get different values. But what are these things? 4x minus 3y equal to 0, or 4x minus 3y equal to 1, or 4x minus 3y equal to 2. These are all lines, and they are lines that with basically, if you solve for y, you see the slope is going to be a positive value, and therefore B is the answer. Another iClicker question. Match the function with its contour map. This time f of x and y equal to y to the third minus y. And pause and answer. So this time you're setting x to the third minus y, let's say equal to 0, or x to the third minus y equal to 1, and so on and so forth, all these different constants. And every one of these are basically, the first one is just y equal to x to the third. The second one is y equal to x to the third minus 1. And they're all cubic polynomials. And out of these three, A is the answer.